Adding same number multiple times becomes tedious as and when the number of times increases. There came the idea of multiplication. In order to add 5 10 times, you just need to multiply 5 by 10. If you see two numbers gets multiplied, say 25 into 400, and you multiply it easily as 10,000, remember, it is a replacement of adding 25 400 times. Imagine how boring and difficult it would have been in the absence of the idea of multiplication. In order to make things easier, I'm sure you might have studied multiplication tables in lower classes. I remember it was a really difficult time for me memorizing a bunch of multiplication tables in my childhood, but later realized, and I'm grateful that somebody compelled me to learn them those times. Consider a square of side 5 centimeters. If you want to measure the perimeter of this square, you need to add the lengths of its 4 sides. You see, it is the repeated addition of 5 4 times. So, it's simply the multiplication of 5 by 4, which is 20 centimeters. Now, suppose you want to find the area of this square. You remember how to find the area of a square or even a rectangle. You just need to multiply the length by its breadth. Being a square of side 5 centimeter, it is 5 centimeter into 5 centimeter, which is equal to 25 centimeter square. Calculation of perimeter caused repeated addition, which made use of the idea of multiplication. Now, the calculation of area of a square leads to repeated multiplication. If you consider a cube, calculation of its volume will lead to repeated multiplication of length of its side 3 times. As the repeated addition gave rise to multiplication, repeated multiplication leads to a new way of representation called exponents. For example, multiplying 2 5 times results 32. But writing this as a multiplication consumes more space and is inconvenient. Thus, a new way of representation of numbers multiplied repeatedly came into picture, called exponential representation. In this example, we can write the product in the exponential form as this. Here 2 is called the base and 5 is known as the power. The exponential representation of repeated multiplications became easier. But now, the new question is, can we use this representation as such in the arithmetic operations, just as we use ordinary numbers? Fortunately, the answer is yes. Based on certain rules, we can operate the numbers in exponential forms easily. For example, if you multiply numbers with the same base, you may just add their powers. This rule is known as the product rule. Also, if you take the quotient of two exponential numbers and if their bases are the same, then you just need to take the difference and write as a single power of the base accordingly. A third rule talks about the nested powers of a base. In that case, it's equivalent to multiplying the powers together and raising the base to this product. Thus, we expressed repeated multiplication in the exponential form using bases and powers or exponents. In 1614, a Scottish mathematician, John Napier, introduced a new way of simplifying complex calculations known as logarithms, which remain as one of the most important advances in the study and practical application of mathematics. Logarithms convert problems of multiplication and division into much easier addition and subtraction problems, and hence mathematical tables containing common logarithms were extensively used in computations until 1970s. So what are logarithms? Logarithms now are viewed as inverse functions of exponentials. For example, we know the exponential number 10 to the power 2 is 100. Here, the exponent 2 is called the logarithm of 100 to the base 10. Similarly, 10 to the power 3 is 1000. So we say logarithm of 1000 to the base 10 is 3. These logarithms whose base is 10 are called common logarithms. In the same manner, 16 may be represented exponentially as 4 to the power 2. So in logarithmic terms, we say log 16 to the base 4 is 2. Note that the same number 16 may be expressed as fourth power of 2. So we say log 16 to the base 2 is 4. From the logarithmic expression, we can go back to its exponential notation easily. For example, log of 9 to the base 3 is 2. In the reverse way, this can be written in exponential form as 3 raised to the power 2 is 9. I think this video will help you to remember the exponential and logarithmic conversions. So keep this in mind. We know any number raised to the power 0 is 1. For example, 10 to the power 0 is 1. This can be expressed in the logarithmic form as log 1 to the base 10 is 0. In the same way, the fact that 3 raised to 0 is 1 may be put in the logarithmic form as log 1 to the base 3 is 0. Or in general, we can say log of 1 to any base is 0. We were able to do arithmetic between exponential numbers using certain rules like product, quotient, and power laws. In the same manner, product, quotient, and power rules are there for logarithmic numbers too. For example, the product law says that the logarithm of a product at any non-zero base is equal to the sum of the logarithms of its factors at the same base. The second law, the quotient law, states that the logarithm of a fraction at any non-zero base is equal to the logarithm of the numerator minus the logarithm of the denominator, both at the same base. And the power law says the logarithm of a power of a number at any non-zero base is equal to the logarithm of the number at the same base multiplied by the power. Thus, we saw how the addition, multiplication, exponentiation, and logarithm are related with each other. But at the time of invention, logarithms' connection with exponents were still not recognized, as logarithms were used as calculation tables. American mathematician Howard Eves said, "One of the anomalies in the history of mathematics is the fact that logarithms were discovered before exponents were in use." E.W. Hobson called the invention of logarithm as one of the greatest scientific discoveries the world has ever seen. That's all for now. Let's meet again with another interesting topic. Till then, goodbye. Have a nice time.